Okay, so this is my title, and so I'll explain a bit about symplectic geometry, what it is, again, if you haven't heard of it yet, and then I'll explain a bit about affine varieties. So, okay. So in symplectic geometry, it had its origins in classical mechanics. So you have some classical physical system, and it has some position coordinates, q1 to qn, and some momentum coordinates, p1 to pn. So you could think of, I don't know, some planets or something. They have a whole bunch of position coordinates and a whole bunch of momentum coordinates. And then at any one point, so at any, if I give you some value of q1 to qn and some value of p1 to pn, then there's some energy of that system. So something like kinetic plus potential energy or something along those lines. So that's given by a Hamiltonian h, which is a smooth function. And then you want to see the motion of the system. So you view these position and momenta as a function of time, and then they satisfy these equations here. So these equations are partial derivatives in the energy are equal to some time derivatives in the coordinates. So symplectic geometers don't look at these equations like this. We look at them like that. So the partial derivatives in the Hamiltonian equals some matrix times time derivatives in the coordinates. And symplectic geometers are sort of interested in this matrix here, basically. So, for instance, if I could change these coordinates to q1 prime to q1 prime and p1 prime to pn prime, and then use the chain rule to change these equations, express it in these new coordinates, and then I would still get derivatives equals matrix and times derivatives. And if these coordinates preserve this matrix, then that's a sort of called a symplectic transformation, and we're interested in that. So, so a simple example is a bead on a wire. It says click to animate, but I'm not going to animate. I'm not going to bother. So you have a wire, and there's a bead on it, and it's got no friction, so the bead just goes up and down like this. And then you want to see what happens to the particle, this bead, what happens to its position momentum. So here you have position, which is how far horizontally, and then momentum, which is the height. So it's the horizontal component of position and the horizontal component of momentum. And it starts here, and it's motionless, so it has a high position but no momentum. And then I run it, and it goes round in a perfect circle like this. But symplectic geometers, we view the whole system at once. We view all the possible initial conditions, and we view this whole plane as rotating around. Okay. So a symplectic manifold, so that's a manifold with a 2 form, and it locally looks like this. So it's a manifold with a 2 form, which locally looks like this matrix here. So another way of saying it is, well, you know, manifolds are defined using chart changes. We require these chart changes to be symplectic, so they have to preserve this structure of that equation, Hamilton's equations. And equivalently, it's a manifold with a closed non-degenerate 2 form, so that's the standard definition. Okay, so now I'm going to talk about affine varieties. Oh, no, I'm not. I'm going to talk about cotangent bundles. So one can think of this bead. My example was a bead on a wire, but you didn't have to think of a bead on a wire. It could be constrained to something else. It could be constrained to some other compact manifold, like a sphere or a torus or something like that. And this is a structure of a symplectic manifold. So here is my bead, and it's on a circle, for instance. And then the phase space is now a cylinder, and the position is how far around the cylinder you are, and the momentum is given by the height along the cylinder. So that's an example of a cotangent bundle. And then there's other more complicated ones. So we could have, cotangent bundle of other manifolds. Okay, so we have an affine variety, and it's the zero locus of some polynomials. And we can view those as symplectic manifolds. So how do we do that? So you have a smooth affine variety, so it's a zero set of some polynomials, and that's some complex manifold. But we view it as a real C-infinity manifold. And we restrict our symplectic form, which is the standard symplectic form on Cn, to this affine variety. And that is, so that's a real manifold with a symplectic form of even dimension. And the symplectic form is actually a biholomorphic invariant. So if you have two biholomorphic affine varieties, then they're symplectomorphic. That's a non-trivial statement, actually. OK. And here's some examples. So this equation, this actually turns out to be a symplectic manifold symplectomorphic to the cotangent bundle of the sphere. And then there's this one. Then there's a more non-trivial example here, which is actually an affine variety which is contractible. And I wrote that down because I like that example very much, but I'm not going to explain anything much more about it. OK. OK. So here's some questions, and they're not they don't exhaust the whole subject area, but so questions are sort of what are good ways of describing affine varieties symplectically? And another question, sort of, I suppose, related is sort of what is the relationship between the sort of algebraic structure of the affine variety, sort of say algebraic invariants and say various symplectic invariants, and what does the symplectic structure remember about the affine variety and so on, and vice versa, sort of what does yeah. So I mean, what does the symplectic structure remember about the affine variety itself? And then there's sort of dynamical questions. So a lot of natural symplectic manifolds are affine varieties. So you could have a natural Hamiltonian on it, and you could ask sort of what are the dynamical properties of this Hamiltonian. And there's also mirror symmetry, which is something I'm not going to explain. But if you want to know more, maybe Nick Sheridan over there can tell you. Maybe. Yeah, I hope so. And other people, maybe. OK. So I'm going to focus on these two things. So this result by Ellie Ashberg, which basically says if you have two affine varieties and they're diffeomorphic, and then the diffeomorphism has to have another constraint, which I won't say, but it's some topological constraint, then C times A is symplectomorphic to C times B. So you have two affine varieties, A and B. So if you cross your affine variety with C, somehow all the symplectic data disappears. And so you might think, well, I suppose maybe after this result, people initially thought maybe it's purely, symplectic geometry of affine varieties is purely a topological thing. And then Seidel and Smith came along and gave examples of symplectic structures on R to the 2n, which are not symplectomorphic to the standard R to the 2n structure. So then it turns out the symplectic geometry is far more complicated. It's sort of it's still pretty rich. It's not just topological. And then my thesis, I extended this result. I said there's actually infinitely many affine varieties, and they're all diffeomorphic to Rn, and they're all pairwise not symplectomorphic to each other. So there's a whole infinite family in each dimension n greater than or equal to 3. When n is 2, by the way, then this statement's false is only 1. OK. OK. OK, so I introduced these cotangent bundles, and one might think, well, is there some way of describing these affine varieties as a sort of motion of a system, like a bead on a wire, or like a bead constrained to some manifold or something like that? And the answer is mainly no. So this is a result, fairly recent result of well, fairly recent. So most cotangent bundles are not symplectomorphic to smooth affine varieties. So if you have and most means the cotangent bundle is very complicated. So say the fundamental group grows exponentially, or the Betti numbers are too big, or something like this. So here are some simple examples. So it turns out these are symplectomorphic to the cotangent bundle of the sphere and the cotangent bundle of the two torus. They're definitely symplectomorphic to smooth affine varieties, and I actually wrote down these equations earlier. But cotangent bundle of the genus 2 surface or higher, the fundamental group is too complicated, so they're not symplectomorphic to any smooth affine variety. So, so somehow these two natural families of symplectic manifolds, they're fairly disjoint. Okay. So I thought I should just explain a little bit about what I'm hoping to do at the IAS, maybe. I'm sort of thinking about what other sort of algebraic and what sort of properties of the algebraic variety are still remembered by the symplectic structure. So I was looking at an invariant called log Kodaira dimension, which is just some integer, and I won't define it here. And I have these partial results, which say sort of that are work in progress about showing that in some sense log Kodaira dimension is an invariant. When I said earlier you have your affine variety and you cross it with C and then everything becomes topological, the point is when you cross it with C, the log Kodaira dimension actually jumps to minus infinity, and so somehow it doesn't contradict what Eliashberg proved earlier. Okay. Okay, I'll explain some of the tools. So two tools I use. The main tool is actually symplectic cohomology. So this is a cohomology theory where it's sort of, I have some nice Hamiltonian. It's a Hamiltonian that sort of, you have your affine variety, and it's a Hamiltonian that sort of grows rapidly. And you have a chain complex which is generated by periodic orbits of this Hamiltonian. Oh dear, I forgot a J. There's a J here. It doesn't matter. It doesn't matter. This is just giving you an impression of what's going on. So, okay. So, so this is the main tool I use. And then sometimes I've used Gromov-Witten invariants as well. So you take your affine variety and you compactify it, and you look at holomorphic curves on this compactification. Symplectic homology I really like. It's cohomology I really like. There's even a version of, if you went to Mike, the talk on persistent homology, there's a persistent symplectic cohomology. So any affine variety, you can get a barcode out of it and maybe extract information about it, which is pretty cool. But I don't know what to do with that yet. But that's pretty cool, pretty good. I think I will stop there.